Hey there, this is day one of stoichiometry. Stoichiometry is definitely not something you can sleep through. So let's get started, shall we? Today we're going to learn to identify mole ratios from balanced equations. You all know how to balance an equation. The mole ratios are obtained from the coefficients, so shouldn't be too hard for you guys. Y'all do great at that. Then we're going to convert moles into moles. So it sounds daunting. It's fine. So what does this mean? What does stoichiometry mean? It's a really funny word. Stoichio is Greek for element, and metry just means measure. So you're measuring elements. Stoichiometry is really about measuring the amounts of elements and compounds involved in a chemical reaction. Why should I care about stoichiometry? Well, there's a lot of things you use that stoichiometry has to be used for. Manufacturing will make sure, let's say we're making lipstick, okay? I'm a manufacturer of lipstick. I have to buy a certain amount of dye for a particular lipstick that I'm going to make. Well, it's important for me to know how much lipstick I need to make so I know how much dye to buy, because I don't want to buy too much, then it will just go bad and I've wasted my money. So stoichiometry is involved in that manufacturing type process. Companies that make products carry out chemical reactions efficiently in order to keep prices down and to maximize their profits. Why did I have to learn how to balance an equation? Well, law of conservation of mass. What you start with, you end with. You have to account for that mass somewhere. Chemists use balanced equations to calculate how much reactant is needed in order to make a certain amount of product. We'll use grams, and we'll have to convert everything into moles. Sometimes we'll use liters. It just depends on what we're going from and what we're going to. So stoichiometry is, we're going to use our cupcake example. Without stoichiometry, there would be no cupcakes. So let's pretend, now I realize you need more ingredients than this, but just work with me here. 5 eggs plus 1 box of cake mix will give me 18 cupcakes, we're going to pretend. So what do I need to make 36 cupcakes? Right, I'm going to need 10 eggs and 2 boxes of cake mix to make 36 cupcakes. That's very easy, very easy. How many cupcakes can I make, though, if I have a dozen eggs and 2 boxes of mix? Okay, I can still only make those 36 cupcakes, and I'll have 2 eggs left over because I only needed 10 eggs and 2 boxes of cake mix to make 36 cupcakes. Well, how many cupcakes can I make if I have a dozen eggs and 3 boxes of cake mix? Well, you still need 10 eggs and 2 boxes of mix to make 36 cupcakes. Does it matter that I have an extra box if I don't have enough eggs? No, it does not. It simply means I'm going to have a lot left over. I'm going to have a lot of cake mix left over and still that couple of eggs. So what if I started with 300 grams of eggs and 90 grams of cake mix? Right, you know what? I couldn't figure that one out either. Okay, I couldn't do that either. I need to convert them into a unit that I can actually use. We use moles. Chemists use moles. After this unit, you're going to be able to answer this question and so many others. Stoichiometry is going to become your best friend. So if I'm given this equation, I'm going to work down here on my document camera. Given this equation, N2 plus H2, so that's nitrogen plus hydrogen, yields ammonia, yields that NH3. Let me put this down here for you. Make sure I've got it in there. N2 plus H2 makes ammonia. Okay, you smarty pants probably have already figured out that thing isn't balanced. So let's balance the equation. I have 2 nitrogens and 1 nitrogen here. So that's not going to work out for me. So I put a coefficient of 2 there, balancing my nitrogens. Well, now my hydrogens are out of balance. I have 6 here. That's easy enough. I'm going to put a 3 there. Now, you don't have to do it, but we're just going to put a 1 there, just so that we have something in every blank for you. We're going to fill in these blanks here using this balanced equation. So how many atoms of nitrogen do I have? How many atoms of hydrogen? How many atoms of nitrogen and hydrogen in the product? Well, looking at just atoms here, let me get a different color. Looking at just atoms, there's 2 nitrogen atoms, 6 hydrogen atoms. On this side of the equation, I have 2 nitrogens and what? 6 hydrogens. So that hasn't changed, okay? That's conserved. Atoms don't change. Those aren't going to change. How about molecules? How about molecules? Well, that's a diatomic molecule. So I have 1 molecule of nitrogen. I have 3 molecules of hydrogen. I have 2 molecules of ammonia. So obviously the molecules don't stay the same. How about moles? I told you in the beginning moles is, we're just going to use the coefficients. So for moles I have 1 mole of N2, 3 moles of H2, and then 2 moles of NH3. Here, let me move that up a little bit for you. How about grams? If we were going to calculate grams, okay, about 2 ammonias would be somewhere in, let's see, 14 times 2, so that's 28 grams of nitrogen. 6 hydrogens at about 1 apiece, so that's going to be about a mass of 6, so 6 grams of hydrogen. And how about over here? Ammonia, so nitrogen is 14, hydrogen is 3, so 17, 2 times 7, what's 2 times 17? 34. 34 grams of ammonia. Okay, so the things that don't change, what doesn't change? Well, you know, our atoms aren't going to change. Okay, things that are conserved. Moles don't change. Moles stay the same on either side. Moles are going to be the same as our coefficients, but they don't stay the same on either side. Neither do the number of molecules. Molecules and moles, neither one of them stay the same. But what does stay the same? The atoms. So atoms are conserved. Atoms are conserved. What else is conserved? Mass. What do you mean mass is conserved? I don't know. What's 28 plus 6? 34. 34 grams. Okay. So mass and atoms are conserved when we're doing these stoichiometric calculations. So let's consider this chemical equation. 4NH3 plus 5O2 yields 6 waters and 4 nitrogen monoxide. What do all these numbers mean? I'll find an eraser. So what do all these numbers mean? These numbers are the number of moles of each thing. Okay, 4 moles of ammonia, 5 moles of oxygen, 6 moles of water, 4 moles of nitrogen monoxide. Recall that chemical formulas represent numbers of atoms. Okay, so that means 1 nitrogen, 3 hydrogens, 2 oxygens, 2 hydrogens, 1 oxygen, etc. Okay, that's what that means. Those are the number of atoms of each one. Look here for NO, 1 nitrogen, 1 oxygen. With stoichiometry, we find out that 4 to 5 to 6 to 4, they do more than just multiply atoms. Okay, with stoichiometry, we use these to call as a mole ratio. We call them a molar ratio. We can write several mole ratios for this equation. Okay, we can write 4 moles of ammonia to 5 moles of, why? Well, look, 4 moles of ammonia to 5 moles of oxygen. 4 moles of ammonia to 6 moles of water. 5 moles of oxygen, yeah, to 4 moles of nitrogen monoxide. Each ratio can become a conversion factor. Okay, we can use it as a conversion factor to convert between units. Okay, whenever we have a balanced chemical equation, we can always convert from moles of one substance to moles of another substance by using this mole ratio, by using the balanced equation as a conversion factor. Okay, 4 to 5 to 6 to 4 can mean a couple of things. It can mean 4 molecules of ammonia reacts with 5 molecules of oxygen to produce 6 molecules of water and 4 molecules of NO. Or it can be 4 moles and 5 moles and 6 moles and 4 moles. Okay, it could mean molecules. It could mean moles. Moles makes more sense. Molecules is too tiny. We use moles. How many moles of water are produced if 2 moles of oxygen are used? Okay, well, let's look and see what we have here. Water and oxygen. Well, here's my oxygen. There are 5 moles of oxygen and 6 moles of water. So I'm going to show you how we do these stoichiometry calculations down below. Make sure you can see that. Okay, I take my given. The given in this case is 2.00 moles of oxygen. Okay, I want to calculate the moles of water that are produced from 2 moles of oxygen. So I'm going to use these mole ratios. Okay, I'm going to first disco down my unit. So I'll take the moles of O2, put them in the denominator, moles of O2. Okay, moles of what I've got, that goes on bottom. Well, what did I want? What am I looking for? Right, I'm looking for moles of water. All right, I'm going to use my coefficients in the balanced equation for this mole ratio. Okay, there are 6 moles of water in my balanced equation and 5 moles of oxygen in my balanced equation. The unit moles of O2 will cancel, and I'm left with moles of water, which is what I was trying to calculate anyway. So 2 times 6 is 12, divided by the numbers in the denominator here. 5 C equals. So what is 12 divided by 5? Let's see, it's 2 and some change. 12 divided by 5 gives me 2.4. Okay, so there are 2.4 moles of water that are produced. Or I'm sorry, that are produced from 2 moles of oxygen. Okay, see how I set up the problem? Get the whole thing, trying to get the whole thing in there for you. Okay, mole ratio is of oxygen to water, 5 to 6. 2 moles of oxygen. See what I did? Same thing I did on my my whiteboard down here. Okay, I use that mole ratio to my advantage, and then I multiply 2 times 6, because I multiply everything in the numerator, and I divide by what's in the denominator, which is 5 in this case. 2.4 moles of water. Oops, let's go back. Correctly balanced equation is essential. I cannot stress to you enough how important correctly balancing your equation is. Okay, if you don't correctly balance your equation, you're not going to get the right answer. How many moles of NO are produced in the reaction if 15 moles of water are also produced? I don't know. Let's see. So what is my given? Right, 15 moles of water. That's my given. Okay? I disco down my unit. If I do nothing else right, I do this right. Okay, this will get me on the right track. So I disco down that unit. What am I looking for? I'm looking for moles of nitrogen monoxide. So I put moles of NO in the numerator. Then I use that mole ratio. How many moles of NO are in my balanced equation? 4. How many moles of water? 6. So 15 times 4 divided by 6, 10 moles of nitrogen monoxide. Okay, pretty easy. Pretty easy. You're going to use that balanced equation for the mole ratio. See, 10 moles. A little neater than mine. How many moles of water can be made using 1.6 moles of ammonia? Okay, well, we're going to start by writing our given, 1.6 moles of ammonia. And then I'm going to disco down my unit. I don't care if you're tired of hearing that. You're going to keep hearing it. Okay? I've got moles of ammonia. I'm looking for moles of water, so I put that in my numerator. I go back to my balanced equation. How many moles of water are in my balanced equation? 6. How many moles of ammonia are in my balanced equation? 4. Okay, I'm going to multiply 1.6 times 6 divided by 4. 1.6 times 6. That's 9.6. And I'm going to divide that by 4. Divided by 4. 2.4. So my final answer, 2.4 moles of water. Okay, so why do we need to convert mass to moles? Well, because it doesn't work if you don't. It's too difficult to work with masses. Moles are easier to work with. If I was given an equation, 2 buns plus 1 patty is equal to hamburger, okay? How many complete hamburgers could I make if I had 10 kilograms of hamburger and 2 kilograms of bread? Well, I don't know either. I know I need to know the mass of the buns and the mass of the patty. That'll make my life easier. So you would first need to know the mass of each individual burger patty and each bun in order to answer this question. How many complete hamburgers could you make if you have 10 kilograms of hamburger meat, 2 kilograms of bread? Look, now I have extra information. Each patty is 0.5 kilograms. Each bun is 0.1 kilograms. So I want to calculate how many patties and buns I have. So I have 10 kilograms of meat total. 1 patty is 5 kilograms of meat, or half a kilogram, sorry, 0.5 kilograms of meat. So, because I just go down that unit, I knew where to put everything. I just go down my unit. Makes sense. Then kilograms of meat cancels, and I have 20 patties. 10 times 1 divided by 0.5 is 20. Okay, 2 kilograms of bread, just go down my bread. 1 bun is 0.1 kilograms. Multiply 2 times 1 divided by 0.1, and look, I had 20 buns. 20 patties, 20 buns. Okay? All right, using the stoichiometry guide, we always use the same type of information to move between steps. Kids, you got to know the moles. Moles is super important. You have to convert everything into moles, or else none of this is going to work out. Okay, you can do that. Let's say we have the molar mass of something. If we convert that into moles of one thing, we can convert it into moles of something else, and then molar mass of something else. Sounds complicated. It sounded complicated when it came out of my mouth. But when I show you how to do it, I think it'll be less complicated. So, how many grams of water are produced if 2.2 moles of ammonia are combined with excess oxygen? All right, well, we're no longer going from mole to mole. We're now going from moles of something to mass. Okay, this is different. We got to convert things into moles to make it work. So I start with my given, 2.2 moles of ammonia. Okay, I want to convert to mass of water. But first I have to convert to moles of water. So the way I do that is I just go down my unit, moles of NH3, and moles of water in the numerator. Because when I use that balanced equation, when I use those coefficients, I can do this. I can go from moles of ammonia to moles of water. So I go back to my balanced equation. There are 4 moles of ammonia and 6 moles of water. Okay? Moles of ammonia cancels. What was I looking for, though? I was looking for grams of water. So watch this. Just go down my moles of water. Okay, you remember in the last unit how 1 mole can equal a number of things? And 1 mole could equal molar mass, right? Okay, what if we did 1 mole of water is equal to its molar mass in grams on top? Okay, molar mass of water, I'm not going to calculate it, 18.015. Okay, 1 mole of water is its molar mass. Okay, this is a legal and fair move. I went from moles of ammonia, converted to moles of water, then from moles of water to mass of water. Now I multiply everything in the numerator. So I'm trying to find a good place to do this. Doesn't look like I'm going to. So let's see, 2.2 times 6 times 18.015. Okay, that gives me 237. I'm going to try to fit it all in here. 237.798 divided by, what's in the denominator there? Okay, it's just 4. It's 4. So I'm going to divide 237.798 by 4. We'll see what that comes out to be. 59.4495. 59.4495 grams of water. Okay, we're not done yet. Yeah, I'm going to make you sig fig it. 2 sig figs in my problem. That means I can only have 2 sig figs in my answer. That's a sig fig, that's a sig fig. That's 2. That 4 does not round that 9 up, so my final answer is 59 grams of water. I can make 59 grams of water from 2.2 moles of ammonia. Okay, you feel smart? You feel lost? That's okay. Do some more. See if we can get you past that. See, look, it even pops in for you. A little bit neater than mine, isn't it? All right, how many grams of oxygen are required to produce 0.3 moles of water? Okay, so let's go by write our given first. We're going to write the given first. You know what? Let's use a different color. Let's go with blue. 0.3 moles of water. Okay, I need to go to grams of oxygen. So I need to convert moles of water into moles of oxygen. So I just go down my unit and put moles of H2O in the denominator. And I put moles of O2 in the numerator because that's what I'm trying to convert to. Okay, once I've got it in moles of oxygen, I know the molar mass of oxygen and I can convert to grams. So there are 5 moles of oxygen in my balanced equation and 6 moles of water. Moles of water cancel. Okay, almost there. Just go down moles. Put moles of O2 down here. Okay, moles of O2. In 1 mole of oxygen, it's going to be 15.999 times 2. That's 31.998 grams of oxygen in 1 mole of oxygen. Okay, moles of oxygen cancel. I've got it into grams now. That's what I wanted. Okay, so I stop and I do some math. I'm going to do 0.3 times 5 times 31.998. And that gives me, in the numerator, 47.997. Divided by, what's in the denominator? Well, just 6. So I'm going to do that math. Divided by 6 equals, look, 7.9995 grams of oxygen. Okay, oh yeah, we're going to sig fig this thing. I can only have 1 sig fig in my final answer because there's 1 sig fig right here. 0.3, that's 1 sig fig. So what am I going to round that to? I'm going to round it to 8 grams of oxygen. My final answer. That's my final answer. I'm telling you, that's what it is. Let's see. Let's click through. Did she get it right? Did she get it right? Oh, yeah, bro, I did. Awesome. Okay, how many moles of nitrogen monoxide are produced from a mass of 13 grams of ammonia? Okay, we're going backwards. Okay, it's okay to go backwards. You can do that. No worries. Start by writing your given. The given is 13 grams of ammonia. Got to convert to moles. Got to convert to moles first. So in order to convert to moles, I'm going to just go down grams of NH3. Okay, and I'm going to convert this into molar mass. 1 mole of ammonia is how many grams of ammonia? Well, let's see. Use your periodic table. 1 nitrogen, 14.007, plus 3 hydrogens at 1.008 apiece, 17.031. You probably didn't see that. It was off the screen. Didn't mean to be. 17.031. Okay, so grams is canceled, and now I've got it into moles of ammonia. Well, now I can use my mole ratio. I just go down moles of ammonia. Okay, and I'm going to convert into moles of NO. Moles of NO. Right? So let's go back to the balanced equation. There are 4 moles of ammonia and 4 moles of nitrogen monoxide. I've converted from grams of ammonia to moles of nitrogen monoxide. Look at that. Okay, we're going to multiply everything in the numerator. So let's see, 13 times 1 times 4 is 52. 52 in the numerator. Denominator, 17.031 times 4, 68.124. 52 divided by 68.124 gives me, oh, a huge number, 0.7633139569. Oh my goodness. How many sig figs can I have? I can have two sig figs. So there's 1, there's 2. That 3 does not round the 6 up. So my final answer, 0.76 moles of nitrogen monoxide. Okay, see if it clicks through and you can get it easier. Oh, no, did not. So we can go back. Okay, so that's my final answer. What do you think? Stoichiometry, the bomb? You know what? You're going to get really good at it, and it's going to be okay. So sometimes we have to go from moles to volume. We learned that there's a conversion factor that we can use from the mole unit. 1 mole of any gas is equal to 22.4 liters. So according to Avogadro's law, we can use that 22.4 liter in our calculations. 1 mole is 22.4 liters, or I might have to go 22.4 liters is 1 mole. So let's pretend. Let's do this problem here. If I know that I have 3.5 moles of neon gas, what would the volume be then? Okay, 3.50 moles of neon gas. Okay, I'm going to use that conversion factor. 1 mole is equal to 22.4 liters. Okay, I just go down moles of neon. And I use my conversion factor. Well, what number is next to moles? It's 1. And I'm converting to liters. What number is next to liters? Right. Okay, moles cancel. 3.50 times 22.4 gives me 78.4 liters of neon. Okay, so we can use that 22.4 liter conversion. Okay. For this reaction, zinc plus 2 hydrochloric acids yields zinc chloride plus hydrogen. What volume of hydrogen forms if 10 moles of zinc reacts at STP? Well, I know I'm going to use liters because hydrogen here is a gas, and that's what I'm looking for. I'm looking for volume of hydrogen. Okay? Given is 10 moles of zinc. So I start out 10 moles of zinc. Okay, I'm going to use my balanced equation the same way. I'm just using a different conversion factor. No freaking out. Okay, I just go down moles of zinc. Okay, and I'm going to convert to moles of hydrogen. Okay, I've got to put everything in moles first, and none of it's going to work if I don't do that. So I go to the balanced equation. There was 1 mole of hydrogen and 1 mole of zinc in my balanced equation at the top. Okay. Cancels my zinc. Now I'm going to use that 22.4 liters conversion factor. I just go down moles of hydrogen. In 1 mole of hydrogen gas, there's 22.4 liters of gas. Okay, we'll put H2 there. Okay, moles cancel, and I've converted into liters. So do that math. 10 times 22.4 divided by 1. Is going to give me, here, let me see if I have enough room, 224 liters of hydrogen gas. There we go. Okay, using the volume of hydrogen in the previous problem, which we still have, 224, we'll write it at the top so we don't forget it. 224 liters of hydrogen. Okay, I wrote it up there. You just can't see it. There we go. Using the volume of hydrogen we found in the previous problem, how many moles of hydrochloric acid were used in the reaction? Okay, well, we're going to start with that as our given. 200, goodness, you know what? I'm tired of writing in that color. Let's see if we can see the orange. I really want to use the orange. 224 liters of H2. And I'm going to convert from liters of H2 to moles of hydrochloric acid. Well, I'm in liters. I don't want liters. I have to convert everything to moles first. So I just go down my unit. I happen to know a conversion that goes from liters to moles. Okay, 22.4 liters in 1 mole of hydrogen gas, and 1 mole of any gas. Okay, I've converted out of liters into moles. Now I can convert from moles of hydrogen to moles of hydrochloric acid. Just go down, moles of hydrogen, and I'm trying to calculate the moles of HCl that's used. So I go back to my balanced equation. Let's see, there are 2 moles of HCl and 1 mole of H2. That cancels. And let's do that math. Okay? Multiply everything in the numerator. 224 times 1 times 2. Hang on, I can't operate my calculator. Give me a sec. 1 times 2 gives me 448. Yeah. And then everything in my denominator, 22.4 times 1, 22.4. Divide denominator into numerator, and I get 20 moles of HCl. Okay, look at how we did that. Lots and lots of stuff. Okay, we're going to stop here. We'll go on to do some more stoichiometry tomorrow. So good luck, do your homework, and do your quiz. If you need help, be sure to reach out to your teacher.